Okay, so I would like to request Kabir and Madhav to stay on a little bit after the class. Of course, anyone else can also stay just for 5 minutes. I want to discuss the notes. Okay, so, all right, so where are we? So in the last class, we were just trying to go through this propagators. And we said that the propagators have a very general form. And we wanted to say that it's enough to compute just a commutator. And from the commutator, you should be able to obtain any arbitrary propagator in any interacting theory, right? And then we said that a physical manifestation of this is a fluctuation dissipation relation that relates the commutator and the anti-commutator. And trivially, if you know both the commutator and anti-commutator, you can write any combinations of the two operators in terms of them. That's very trivial. So essentially, the fact that the fluctuation dissipation relation relates the commutator anti-commutator, the physical interpretation of this is that the commutator governs dissipation and the anti-commutator governs statistical fluctuation, and these are connected. So we didn't prove that we haven't proved yet that indeed the commutator governs fluctuation, but we will be getting there in the class today. And then I talked about this technology of 1 pi versus 2 pi quantum effective action. And I said that in quantum mechanics, you have this nice technology by which if you just want to see the evolution of the 1-point function, you can construct a quantum effective action whose thing gives you this, right? But then from here, you cannot obtain, say, x squared t. So to get all these higher orders so basically what you need to actually compute is a probability distribution for a measurement of xt, right? You want to get this entire problem, not simply the expectation value. To get that, you have to get sequentially higher order functions. And this is something, so to get the next thing, what you should do, you should take x of t, rho of t prime, which is the commutator, and f of t prime, this is the anti-commutator, and write down an action for these three objects together, and whose extrema would give you the evolution of this three. So even if you want to get x squared t, you have to consider, you cannot just leave away the commutator, because x squared t can be obtained from just f t prime and taking the limit t prime goes to t. But still you need to do all of these three things together. And then there is this technology by which you can construct such an action and do this. One interesting comment that I want to make is that in a certain limit, this 2 pi effective action actually reduces to the Boltzmann equation that you already know. So there's a certain limit which reduces to usual kinetic theory. But this is a very powerful formalism because there are cases where usual kinetic theory doesn't work, right? If the interactions are strong between the particle, if quantum effects are large, the quasi-particles are not so well defined, then your usual Boltzmann kinetic theory doesn't work at all. And then you have to go to this quantum thing. But this actually, you can also apply in statistical physics in general, because you can take the h bar goes to 0 limit of this equation, and that gives you statistical physics or statistical physics and statistical mechanics in real time, because usually you have done statistical mechanics already putting the system at a finite temperature, but you can also do that in real time, right? So this is what we discussed yesterday. And then we said that if you take any 1-point function of any operator, which may or may not commute with the Hamiltonian in thermal equilibrium, its expectation value has to be time independent. We proved that. And I gave you a similar problem, which will be in the assignment. The assignment will be either today or tomorrow. If I take a 2-point function, any 2-point function, then it will be in thermal equilibrium, it can only be a function of a difference. And then I showed this beautiful relation, which is that this relation, that is the origin of all the fluctuation dissipation relation, is simply that this g greater t minus I h bar by t gives you G less ABT, ABT, okay? Where G greater and G less are simply defined what we did it earlier, right? And these gives you this. And then what we said is that the G greater AB omega is actually, okay, in Fourier space, it gives me this, provided this object G greater T is analytic in this strip, which extends from imaginary T is equal to 0 to this thing. And this followed from the general spectral representation, which we discussed. So this is a general spectral representation. And using this formula, we analyzed the analytic continuation in time. And we showed that if the convergence of this summation is governed by the exponents, then this will be convergent. These exponents would be convergent when you have these things to be followed. That imaginary time. So we get this when this condition is satisfied. So therefore, from here we can actually prove that indeed that this KMS condition is true, which means that we could indeed do this analytic continuation of the contour and get this result from there. G greater AB omega is equal to this times G less AB omega, right? So this is what we did last time. I also asked you to check that you go back to the quantum harmonic oscillator and check that this is indeed true, because we had explicit expressions for these guys. Have you checked that? Who has checked it? Anybody has checked it? Yeah, these things actually take a minute or two, so you should have done it before coming to the class, because then actually you have to really think about these things, otherwise you don't really learn. It's not about just attending lectures, you know. Okay, so you can go back here and check. Actually, this is true. Okay, I had written down expressions in real time at some point in the class yesterday. I have to look into there. Yeah, so this is expressions in real time. And indeed, if you take G greater xxt and replace it by T minus I H bar by T, then you should be able to get G less. That's easy to check. And also, if you go in real in Fourier space, that also is true, that G greater and G less are related. Okay, so then using these things, it is easy to say that, yeah, so we were able to then compute the fluctuation dissipation relation using this, because rho of omega is I of G greater minus G less. The commutator is nothing but I times G greater minus G less by definition of these guys. And then it follows that the commutator is I times e to the power h bar omega by T minus 1. And the anti-commutator similarly has e to the power h bar omega T by T plus 1. And if I take this ratio, I get half cot h bar omega by 2T. And if I take the limit h bar goes to 0, I get the classical Einstein relation, which is that, like, for example, for the Brownian motion, x squared T has to be D times T, where D comes from this limit rho omega by h bar omega, which will actually show today that this is the right limit to take, where you get dissipation. You get a dissipative coefficient. I will show you exactly today in an example today. Okay, so this is the origin of the statistical mechanics fluctuation dissipation relation. But what we'll do today is to understand there is also a fundamental meaning of omega rho omega. Okay, this is something that that is useful. So to do that, let us try to go back to the spectral representation that we just said. Actually, the spectral representation that I gave for G greater AB is simply this. It is minus I by G sum nn prime over all energy levels. And we assume that all energies are positive because anyway, only what, yeah, so that okay, that you can always do that. You can always, if the all energy levels are not positive, you have a little bit of an issue anyway for for convergence. So, okay, we can always take the ground state energy to be 0, remove the factor of half, and then, and because that's trivial, and then you can take all the energies to be positive. Otherwise, it's simply an overall factor that sits outside. But anyway, this is for interacting theory. This is not for the harmonic oscillator alone. So then you get this expression. And now if I do a Fourier transform of this, it's very easy to see what I get, right? If I do a Fourier transform of this, you will see that G greater omega, let's say AB, would be equal to well, it is simply minus infinity to infinity dt e to the power I omega t G greater ABT. And the answer is simply, I think, minus 2 pi I by Z, because the only dependence comes from the e to the power I En minus this thing. So delta En prime minus En plus h bar omega. Okay, that's what we get, right? Because here we had e to the power I En minus En prime by h bar t, right? So and then we are and then we have here e to the power I omega t, and therefore I think this is a mistake. Maybe this should be En minus En prime. I probably En minus En prime probably. Okay, you can check it. This is then it is N B. Yeah, I think what I wrote is correct. Yeah, then A N prime and N prime B N, right? This is what we showed last time. Okay, so this is G greater and G less. Of course, you can follow the same route, or you can, it should be e to the power simply h bar omega by t times G greater. Sorry, is it? Sorry, G greater will. Okay, sorry, the other way around. It should be, because G greater omega was G greater was e to the power h bar omega by t times G less. So G less should be to the power minus h bar omega by t times G greater omega AB, right? And that is general, but you can also do the same exercise which we obtained to get this expression. Like we just took the basic definition and continued. So you can also do the same exercise, and independently you can see this is nothing but 2 pi I by Z sum n prime e to the power minus En by t again, but now you have delta En prime minus En plus h bar omega, and then the same object N prime and N prime Bn. So one interesting thing is that if you do I times G greater AB omega minus G less AB omega, so this gives you the commutator rho omega in Fourier space, in frequency space, and this is nothing but 2 pi by Z. And I think if I do it correctly, so this would be a homework problem to actually do it. So here actually you can do some steps which I'm omitting, and you get e to the power minus En by t minus e to the power minus En prime by t. I hope I'm doing the algebra correctly. And then delta En minus En prime plus h bar omega. And then you have this thing, N prime, N prime, Bn. So I will take a special case when A is equal to B is equal to, say, X, but it can be anything. So if I now replace it by XX, for example, one thing you see that this becomes a mod square, right? This is nothing but mod of NA N prime X square. So this is positive, right? This is positive. And one interesting thing you see that En, so suppose omega is greater than 0, right? If omega is greater than 0, then we get e to the power minus En by t minus e to the power minus, so because of delta function, we have En minus En prime, but En prime has to be equal to En plus h bar omega. by t, right? So this is what we get from here. And because omega is positive, this guy has to be greater than 0. This weight is greater than 0, right? Are you following? Yes or no? Can somebody respond? Have I lost you already or what? Sorry, I can't hear you at all. Can somebody just respond and say something?
It's fine, sir.
Yes, sir, it's fine.
Thank you. Okay, so sometimes I need this confirmation because I don't understand. So, okay, so En by t minus En prime by t, and then I said that, so this is also an exercise, will be in the assignment to get to here. I mean, this is very easy. You just simply combine these two expressions and do some relabeling of n and n prime, and you will be able to arrive here. And we see that for omega greater than 0, this thing has to be positive because of the support of the delta function. And similarly, for omega less than 0, this thing is negative. So what we show from here, rho omega is greater than 0 for omega greater than 0 and less than 0 for omega less than 0. Okay. And then the other thing you can easily see from this expression that rho omega is real, right? That's obvious from this expression that rho omega has to be real. And also the other thing you can see that rho omega is equal to minus of rho minus omega. That's also is very easy to see from this expression. Okay, so if you just take omega to minus omega, you can relabel n and n prime, you get minus of the same thing. Because this is symmetric in n and n prime, but this is odd when you interchange n and n prime, this factor. So then you will see that these things are true, right? Rho omega is real, and rho omega is equal to minus of rho minus omega. Okay, and so these are the interesting properties of rho omega, and we will see this is enough to. We will see it is very important to get some nice physical interpretation, so, which I'm coming to. But for the moment, these are simply mathematical properties of rho omega. Let us see something more generally. In more generally, it is easy to. We could have also answered. So this is some that so another thing is that when I said that in general the retarded function will have all these poles and branch cuts, so that's a general form that we will show. But what it basically the origin of that form comes from this expression. Then you put in one particle and multi-particle states here. You can say something about what's the general structure of the spectral function. So this spectral function, as I said, is a very important object because the commutator, and from here you can obtain everything else, right? That's what we said. So okay, we are going to go there today, but for the moment we are seeing these properties of the spectral function. So there's another. So all of these you could have also obtained from a very from another way, which I'm going to sketch. And I think it's a very simple exercise. You can think of it as a nice puzzle and do it on your own. So the simple exercise is as follows: that let us even go back to the basic definition of rho. Rho of t was simply the thermal expectation of, say, xt x0, right? And if I take rho star t, right, that would be equal to essentially the dagger of this, right? Because I'm not going to prove it. You can easily show because there's a trace of e to the power minus bht, and because of cyclicity of trace, this would be nothing but the dagger of this object. But what happens if you take the dagger of the commutator? It becomes simply minus of itself. So this is minus of rho t, right? The another easy property that you can see is that rho minus t will be equal to x0, sorry, x of minus t x0, right? And if x of minus t x0, right? And then by translation invariance, which we showed by time translation invariance, I can make this x0 and x minus t, or x0 and xt. So sorry, let me. So I simply add plus t to both of these arguments. I add a plus t here and add a plus t here. So because of time translation invariance, it will be invariant and then becomes this, right? but this is equal to nothing but minus of rho t, right? So we get the following things, that rho star t will be equal to rho of minus t is equal to minus of rho t, right? This is the general property of this thing. And all of these, if you put together, will also imply that rho omega is real and odd function. So you see that rho omega is real and odd from this argument, but without the spectral decomposition, you will not be able to show that rho omega is greater than 0 for omega greater than 0 and omega is less than 0 for omega less than 0. So the only extra information you get is that from the spectral decomposition, the rho omega is positive for omega greater than 0. Okay, so this actually is a very simple exercise. Try to think on your own and do it. So if in real if in time, if this is a property of a function, then you should have, so rho omega basically is purely imaginary. Actually, rho star t is equal to minus rho t would mean that rho omega is purely imaginary in real time. But when you do the Fourier transform, rho omega has to be real and an odd function. That's that you can put together here. Okay, so that's sort of easy. Yeah, because yeah, if rho star t is equal to minus rho t, it means what? It means that your rho is a purely imaginary function, and then it's an odd function also. It's an odd and purely imaginary function. So its Fourier transform is real and odd function. Okay, so try to do it on your own. All right, so this is something that we need for what I'm going to show now. So what is beautiful is as follows, that so now we want to show something called a very fundamental relation, and I give you a very beautiful physical interpretation of it. This is called the sum rule, the spectral sum rule. And this is very fundamental, and it's really beautiful. So the spectral, so if I want to know what is rho of t in real time, I would simply do the inverse Fourier transform. That is obvious, minus infinity to infinity, and I then do d omega by 2 pi e to the power minus I omega t rho of t. This is my definition of the inverse Fourier transform. I'm using it consistently everywhere. Sorry, rho of omega, my typo, rho omega. Now it trivially means what? It trivially means that if I want to compute at rho of 0, right? If I just want to compute at t is equal to 0, maybe I should put explicit. What happened? I always, I don't know what happened. How can I get rid? Oh, okay. Okay, so what happened to the pen suddenly? Oh, bad. Okay, hopefully, no. Suddenly my pen changed. I don't know. Okay, maybe this is what I was having. Okay, then rho t is equal to 0 would be equal to simply minus infinity to infinity d omega by 2 pi times rho of omega, right? So this is trivial. Now suppose I want to compute the time derivative of this function rho dot of t, right? So what I should have, I should simply have minus infinity to infinity d omega by 2 pi and e to the power minus I omega times e to the power minus I omega t rho omega, right? This is what I should have. All right. And so now if I want to compute rho dot of t equals 0, the time derivative at t is equal to 0, I have some simple relation d omega by omega, d omega by 2 pi. You'll see why I'm doing all these exercises very soon. I simply have this as a thing. Now, the interesting thing is this is very easy to evaluate. Exactly. The point is, we know this left-hand side, we know this object for an arbitrary interacting theory. Right? So there is something that I can say about now why we know this for an arbitrary interacting. That we can see easily because rho of t, the definition was the expectation value of this commutator. What is rho dot t? Rho dot t is expectation value of x dot t, right? But x dot t is pt by m x0. Now at t is equal to 0, it is simply the equal time commutator of p and x, right? So this has to be 1 over m times I h bar in any theory, even in interacting theory. Because even in interacting theory at equal time, this is a commutation, is a fundamental commutation relation between p and x. That's not going to change. That's the definition of operators. So what you can say is that if I put it back, so you see that rho dot, I just put in
I thought,
minus.
I have a question, sir.
Yes, yes.
I thought x of t is p of t by m is only in free theory or something. I thought it will be non-trivial, some non-trivial relation in interacting theory.
Why?
I mean, I had no reason.
Okay, so normally in field, normally the way you write the Hamiltonian is a half x dot square, and this is also true in field theory. Plus, you don't use higher time derivatives, right? Yeah. So this is the Hamiltonian. It's a fundamental Hamiltonian that you start from half m square omega naught square x dot square, and then some v extra x, right? So that would have some, but the Heisenberg equation for x dot is simply always p by m in any, because that's not going to change.
So like if you take the classical Hamiltonian of interacting theory and write the Hamilton's equations of motion, you'll get the same equations of motion any Hamiltonian you take.
No, the point is that the equation of motion for p would be different in an interacting theory.
Yeah, but
okay, just let me complete. The point is as follows, that the fundamental theory is supposed to be only two derivative in time. If you have higher derivatives, then the problem is that you need more degrees of freedom. It's not the standard way to think about it, right? So now in the quantum effective action, when you construct the quantum effective, which I mentioned before, you get higher time derivatives also. But that's a separate thing altogether. The quantum effective action should be thought of as a classical object, not as a quantum object that you are quantizing. So that's simply an effective action to compute the equation of motion for x of t. So that can have a lot of non-trivial properties. Yeah, that can have a higher time derivative equation actually. And the interpretation of the higher time derivative is coming from that. Okay, it comes from the following thing, that actually x of t because in the quantum case, as we said, the x and p doesn't form a closed system. You have x squared t, x cubed t, whatever, right? You have this higher order stuff. So now basically you're sort of integrating out in some sense all of this higher order stuff and writing it terms only in one thing, right? If you do that, if you integrate out, then you always get higher time order derivative. It's very simple, right? You take two coupled harmonic oscillators, which has two time derivatives. You suppose you integrate out one of them. By integrate out, I mean that simply solve I don't know whether you have done it. Okay, just simply suppose x and p. X and p has first order equation. But if you eliminate p and you substitute it in the equation of x, equation of x becomes second order. So similarly, if you take two second order equations that are coupled to each other, you eliminate one and substitute another, you get a higher time order equation. So in the quantum effective action, you get a higher time order equation simply because integrating out the quantum fluctuations and writing it out in that way. But the fundamental equation, the fundamental operator equation for x is still the same. It's the Hamiltonian that you're starting from.
Because they're conjugate variables always.
Yes. So that should be true in any theory, and even in quantum field theory. So this object is then on the left-hand side nothing but minus I h bar by m, because the commutator of p comma x is nothing but minus I h bar. And its expectation value of 1, thermal expectation value of 1 is also 1. So this is what we get. Minus I h bar by m has to be minus infinity d omega by 2 pi minus I omega rho omega. And therefore we come up into a nice sum rule The sum rule is that it's true for any interacting theory, any arbitrary theory, that d omega by 2 pi omega rho omega has to be exactly h bar by m. Okay, so let us try to go back and see what is the case for the. So if you see what was if you go back to these expressions for the quantum harmonic oscillator that we derived earlier. So let's see. What the hell? Yeah. So we had this expression for G greater and G lesser for the quantum harmonic oscillator. And if you take G greater minus G less and multiply by I, what should we get here? So you get I G greater minus G less omega, which is equal to rho omega. Here you can do the exercise and you will get, so I think, so pi by m, let me write it down, maybe. Yeah. So for the quantum harmonic oscillator, for the free theory, you got that rho omega, if I, correct me if I'm wrong, pi h bar by m. If we miss something, we can easily understand because of the sum rule is strict, by 2m omega naught. And then we have delta of omega plus omega naught. I'm sorry, this should be delta of omega minus omega naught, I think. Minus of delta omega plus omega naught. So all these other factors will cancel out. You can see, you get this rather simple relation, pi h bar 2m omega naught delta omega minus omega naught and minus delta omega plus omega naught. Okay. So you can see that it satisfies the sum rule because, well, if you do this integral, it is easy to see. We should be able to get the sum rule. 1 second. I think there is no fact. Is there a factor of 2? I think there is no factor of 2 here. Okay, let me fix it. You can also go back and check from the explicit expression. Let us do this integral minus infinity to infinity omega by 2 pi omega rho omega. Well, omega rho omega would mean that I can simply, because it's the first term would give me, if I do this integral, let me do it directly. So omega rho omega, so first will give me an omega naught and the next will give me a minus omega naught, right? That's all. Because there's delta omega minus omega naught, delta omega plus omega naught here. So I get omega naught minus 2 omega naught. So I get twice omega naught from this integral. And there's a factor of pi h bar by m omega naught, and overall factor of 1 over 2 pi. So if I take into account everything, then omega naught cancels, pi cancels, 2 cancels, and I get exactly h bar by m. So this is the correct form. So this is what I should have, okay, for the free theory. Now, if you go to the relativistic invariant case, then omega naught is, okay, I can write this in a better way. So you see that another way to write, so if delta omega square minus omega naught square can be written as delta of omega minus omega naught by 2 omega naught minus of delta omega plus omega naught times 2 omega naught. Okay, this can be written in this way because sorry, wait a second. 1 second. Okay, anyways, so okay, I'm coming to this later. Maybe the first thing to say here should be that you see easily that when omega is great, because see, omega naught by definition is greater than 0, right? By definition, the omega naught is greater than 0. That's how we have defined this fundamental frequency. So this omega minus, so you see for omega greater than 0, rho is greater than 0, and for omega less than 0, rho is less than 0, because you have a minus sign here. Because of the minus sign, when omega is minus omega naught, when it's a non-trivial value, so that's negative. Okay, so now we can give a nice physical interpretation to this guy rho omega, okay? So if I look at omega rho omega, this is what? This is nothing but pi h bar by m, because I can cancel omega naught because it's I can, so it is simply delta omega minus omega naught plus delta omega plus omega naught, right? All right. What I would do is that I would basically do another manipulation, which is I would take 2 pi h bar by m out, and then rewrite this as half times delta omega minus omega naught plus delta omega plus omega naught, right? So why I'm doing this manipulation, it should be clear later. So what I'm going to now say is that, right. So if I do this, if I look at this object, m by 2 pi h bar omega rho omega, for the free harmonic, for the free theory, it is simply half of delta omega minus omega naught plus delta of omega plus omega naught. Okay, this is what it is. Oh, sorry, somewhere I forgot to write. Oh, there is no 2 omega naught now. Okay, because it's this has gone and simply this. So we have, so now it is clear if I integrate this object, and that is what should happen for a general theory. If I integrate, so if I integrate, 1 second, if I integrate d omega minus infinity to infinity of into m by 2 pi h bar of omega rho omega, this object, I get nothing but equal to identity, right? This is exactly what should follow from here. I just simply multiplied this object, and so I took this thing here. Anyway, so now this object, if I plot, right, it looks like this is always positive. So omega rho omega is always positive, and we have two delta functions at omega and minus omega naught. All right, that's what we have here. And when I integrate it, I get 1. Okay. So what is the nice physical interpretation of this? So you'd see it in a general interacting theory. In a general interacting theory, we should also have, because of the sum rule, minus infinity to infinity d omega 2 pi m by h bar. Oh, sorry, m by 2 pi h bar. Let me see. When I integrate this, I also get 1 for any general interacting theory. And the interesting thing is that these object, omega rho omega, is always positive, because you see that rho omega is positive for omega greater than 0, which we showed, and rho omega is negative for omega less than 0. But omega rho omega has to be then positive for all values of omega. So what do you expect it to look like? So in an interacting theory, this, if I plot this object, it should look like this, right? So here it was just simply two delta functions at omega naught and minus omega naught. So this is omega, and this is m by 2 pi h bar omega rho omega. If I plot this, I get, I should not get these two delta functions. Instead, what I should have is, we expect something like this, right? Some kind of broadening to happen, say. Or it could be something very different, right? It can also transform into something very different. But if you just have a small interaction term, that is what you expect. It will get simply broadened out a little bit. So what should be the physical interpretation of this? Can somebody tell me now? Like what, how will you like to interpret this in a physical way? Okay, so the nice physical way to interpret this is as follows, that Suppose you had a harmonic oscillator, right? In the classical physics, the harmonic oscillator x of t was obeying this equation. It is some cos omega t, omega naught t plus some sine omega naught t. And even in quantum physics, that is true. The expectation value of x of t will always take some form of that kind, right? Even in quantum physics also, it should take a form of this kind. This, you can think of this as some a star e to the power I omega naught t plus a e to the power minus I omega naught t, right? This is, so there are two frequencies. One is omega naught and the other is minus omega naught. These are the two fundamental frequencies, omega naught and minus omega naught, when you go to Fourier space of the harmonic oscillator. Now, if I take x of t in an interacting theory, I don't expect, when I go to frequency space x of omega, I don't expect it to be supported only at omega naught and minus omega naught, right? I don't expect it. Instead, what I expect is that I would have some kind of a broadening, right? So now you see that this object that I'm integrating, it always integrates to 1, and this is always positive definite in the interacting theory too. So the interpretation of this can be easily given as this is the probability for the oscillator to not to have the frequency omega naught, but something else.
So could you repeat
And
that? What exactly?
it's a probability, because this is positive definite, integrates to 1. You can interpret it as a probability density. And it's a probability that the fundamental frequency omega is not omega naught, but something, it's omega, right? So probability. Now, if you go to quantum field theory, so what are these? What is this object? This object would be simply, you will have the relation would be true for all frequencies k, because you have a harmonic oscillator for all k, right? So in a general case, you will get this relation omega rho omega k equals 1. Of course, this extra factor is not there because there's an analog of m there, but we will see. I mean, is essentially this factor is just simply 1 over 2 pi h bar, because in the case of the quantum field theory, your Hamiltonian is simply half phi dot square. Your Hamiltonian density is simply half phi dot square plus half grad phi square, right? Which becomes k square phi square, but plus some interaction terms, the m square phi square plus other stuff. But here there is no analog of m, like x dot squared by 2m, there is no m is set to 1. So actually in that case, in quantum field theory, you have no analog of m. Instead, there you get this. And the interesting thing is as follows, that what is the meaning of this is as follows. So this is because of interactions, your particle will not have these frequencies, omega naught and minus omega naught k, right? Similarly, if you compute expectation value of phi of omega at k, right, you will see that it has this two, just like for the harmonic oscillator. If you compute the classical expectation value or the quantum expectation value in the free theory, it will have only e to the power minus I omega naught k t and e to the power I omega naught k t, right? This simply follows from the classical equations, and also from the quantum case, this is true for the free theory. But however, interacting theory, so the particles will not have these. So one of them could be thought of as a particle with energy omega naught k, and the other will have the energy minus omega naught k, right? And so these are the two frequencies where they get subsupported, and then because of interactions, you will expect a broadening. And you see, and what we will see that this is interpretation of an antiparticle, or not really the antiparticle. I will make, okay, when we go there, I'll make it clear. So basically, we have these two frequencies, omega naught k and minus omega naught k, and each of them would be broadened. So the interpretation is that omega rho omega actually tells you the probability that the particle, if you specify the energy k, it will not have a definite energy, but it will have some energy of some form. And that comes because a fundamental particle, because the quasi-particle is decaying, right? In the medium, it can decay to multi-particle states. And any decaying particle cannot have a fixed, very well-defined energy by the uncertainty principle. That is something we already saw. So this width comes from the. So this width tells you the smaller the width of here, the more long-lived the quasi-particle is. The smaller the width here, the more long-lived the quasi-particle is. And so for the for the quasi-particle approximation to work, or something like a Boltzmann description to work, the width delta omega by omega naught should be much less than 1 for the quasi-particle. So then you can describe it using a kind of a Boltzmann equation. So you can think of it as a weakly interacting gas of particles. So whenever this is invalid, whenever this is not true, you cannot use a kinetic theory-like description to describe the system. And you have to use something much more deeper. You have to really use quantum dynamics, not a Boltzmann equation anymore. Okay, so this is essentially the crux of the matter. So actually, as I said, at some point I will give you an exercise. So this is something that you can also see directly from photoelectron spectroscopy. Like this interpretation would become even more clear when you go to photoelectron spectroscopy. Actually, this is exactly the amount of particles that are coming out. So you can, anyway. So we got a good feel that it actually captures some kind of fundamental property of the theory, right? So the measurement of rho omega k is very fundamental. Now, if you are in vacuum, right? If you are in vacuum, and suppose if you are an electron in the vacuum, so the electron field or some electron Dirac field spectral function, there's similar objects. So I should probably not talk of the electron because electron is a fermion. So let me call the Higgs boson spectral function. That's also not a good idea to talk of the Higgs. But I don't know what's a good example to give. But anyway, let me start with the electron itself and pretend it's a boson for the moment. If you look at the electron spectral function, obviously what happens is as follows. So you will see the following thing. You will also see a delta function here, because in the vacuum the electron is stable, it cannot decay, right? Because of simple kinematics, what it can decay to, it cannot decay to anything. And but you see that the pole here has a strength less than 1. It has a pole Z. And then what you will see, there is a big bump like this. And this comes from multi-particle states. This starts at something like 4m square. Or yeah. So where you find this threshold, and this threshold comes from the contribution, this incoherent, this is not a peak, it's something very broad and incoherent. And this comes from the multi-particle kind of states. So in general, what you will see something, but you also see some incoherent background on top of this. So there will be, of course, like this, and then there will be a big incoherent background somewhere. So this is just this incoherent background comes from the contribution of the multi-particle states, from the branch cuts, which I told you in the last lecture. Okay, so this is a structure, and this is something that we will prove. Exactly, this is something called the Callan-Lehmann representation. Or so this is a statement in vacuum. We are going to prove this, but not today, another time. And actually, this would be the basis of understanding renormalization, because it's an exact statement in the field theory. And now, so this Z is called the wave function renormalization, and the mass, of course, will not be the actual mass the mass can be altered because of the fluctuations. It's not what you call the bare mass that appears in the Lagrangian of the theory. It's something that renormalized by, and this is the wave function renormalization that should satisfy this property because of probability, because of this fundamental relation. And then these incoherent background will be the other contributions that you cannot interpret it. So this is going to be the general structure that you expect in your quantum field theory. And this is understanding this is fundamental to understanding what you mean by renormalization, or why renormalization, what is renormalization. So this is something that we will come to later. But that's something like this is also true in quantum mechanics, right? Even in quantum mechanics. Okay, all right. So now we should move on to this. Move on and just say that. So we showed that G greater AB omega, G greater, say XX omega is equal to e to the power R H bar omega by T G less XX omega. But from here, we also showed So you can actually write all these things in terms of the spectral function is obvious. So you can show that G greater XX omega should be equal to, I think, minus I rho XS omega by e to the power, I think it is 1 minus e to the power minus h per omega by t, and G less XX omega. So you can always write your G greater, G less like this. It's obvious, right? Because G greater minus G less is going to give you rho omega, I times that. And you know this relation, so you can easily solve this algebra. And this is very general. So you can also see that this is nice. G less x omega is actually equal to minus I rho x omega times NB omega, the Bose-Einstein distribution, NBE omega, because this is nothing but 1 over h bar omega by t minus 1. This is a Bose-Einstein distribution function. And then G less, G greater xx omega is equal to minus I rho xx omega into 1 plus NB omega. So when you take the difference, it simply gives you rho xx omega back, right? That's obvious. And if you put a k dependence in a general quantum field theory, it will have a k dependence. So it will have omega k. And similarly here, it will have an omega k. But no k dependence here, of course, because the function of omega alone. And because for each k, you get the harmonic oscillator. And for each k, it will be true. So these are the relations that that should be there everywhere. Okay, so now we have to give another. So we see that rho omega has a very interesting kind of interpretation in terms of energies. Now, so suppose the spectral function rho is of a fundamental field, say phi dot, for example, phi, a fundamental scalar field. Then you have phi of x t, phi of x prime t prime, right? Expectation value of that, and that is rho of t t minus t prime and x minus x prime, say. So that would be the case. But here you see it's a fundamental field that we are talking about. So in that case, it has this nice interpretation. When I take rho omega k, the Fourier transform times omega has the interpretation of the probability the particle with momentum k has energy omega, right? This is what we said. But suppose instead of phi, instead of elementary field, you have a more physical observable. For example, you are talking about the charge density, or say the number density, or just the mass density, charge density, or any kind of such densities. Then of course these would be quadratic in phi square. So you'll be talking about something like this. And in this case, we are related to this conductivity and all of these things that we are going to talk about. For example, the electric current, if you take that, will relate to. So when you talk about the fundamental field, it has this very nice interpretation of in terms of the energy. And in fact, what we will see that G less is something that you can measure using photoelectron spectroscopy. The fundamental G less can be measured. But you can also measure if it is a composite operator made out of fundamental fields like phi square, then you can also measure that, and that is related to the to your dissipation. Okay, so we will show it today now. But before that, let us try to see some more more interesting properties and some mathematically, and then I will come to this. So. Right. So up to here, we are all good. I mean, you're following. So I think this is not that hard. I mean, these are all very elementary stuff, but This is not like too difficult maths. I think this is very easy maths. Okay, so now let us go back to the definition of GR AB TT prime, and we defined it like this. It is minus I. So I didn't put the I over H bar here for whatever reasons, and we have AT B0. So this was our definition, and but this is nothing but simply rho ABT, right? And this is minus I theta T. All right. So if I now go to Fourier space, right? So this is GRT only, not T prime. If I now go to Fourier space, what I should have? If I go to Fourier space, I should have, again, I use the convolution. I should have d omega prime by 2 pi, and then the Fourier transform of minus I theta T, right? And what is this? The Fourier transform of theta T is 1 by minus I times 1 over omega plus I epsilon, right? But this minus I gets cancelled. And so we have omega minus omega prime plus I epsilon and the Fourier transform of this rho AP omega. Sorry, rho AB omega prime. Yeah. So now, if you remember, we have this nice relation that 1 over x plus I epsilon can be written as the principal value of 1 over x, right? And minus I pi delta x, right? I hope you remember this, that we explicitly saw that it's basically a regulated version of this, so people can write delta epsilon and p epsilon, the regulated version of this object. Anyway, so then if you put it back here, you see that I can also write it in this way, that GR AB omega. So now, okay, let me now go take this example where you have only x here, the same field. In that case, this is T omega prime by 2 pi, and P of 1 over omega minus omega prime times rho AB omega prime. This would be the real part of your GR. And because rho AB omega is, we know that rho AB omega is real and odd function with and also positive when omega is greater than 0. All this is given. So now if I put it back, so you see that minus I pi and pi and this thing goes away. So I have minus half minus I by 2. And then I have a delta function of omega minus omega prime, right? So it simply gives me minus I by 2 rho XX omega, right? So from here, we learn that rho XX omega is also minus twice of the imaginary part of GR XX omega. Okay. So the spectral function is related to the imaginary part. And the interesting thing is that because GR omega is real, because the retarded propagator is not real, it's complex, but in omega, but GR omega is analytic in omega for imaginary omega greater than 0 because of causality, right? This is something that we discussed, because GRT vanishes when t is greater than 0. That implies it has to be analytic in omega in the upper half plane. So in this case, what it implies is that so you'll see that we get this real GR omega has to be equal to. Now I put in this rho omega is equal to minus 2 imaginary omega. I put it back here, so I get minus d omega by pi. P of 1 over omega minus omega prime times imaginary GR omega, right? So this is another, but this is something that you can also derive very generally. This has to be true simply because it follows from the fact that it is analytic in the upper half plane, right? So if it is analytic in the upper half plane, that you should be able to do this actually in generally. Yeah, try to think about it as an exercise. And maybe I will also give it to you in the assignment. It's very easy. I mean, just think about it. I don't want to say everything in the class because I hope that you will. So sorry, this is imaginary GR omega prime. Okay, so this is a nice relation that you can show very generally. It simply follows from this, and so we see that if we know if we are able to compute rho omega, then we are able to also get the retarded propagator, right? So that's a very nice a very nice thing to learn. And actually, there is also a very nice exercise to do. If you go back to the spectral representation of omega, I can put it back here and write it in this way. I just use the spectral representation of rho AB omega prime here there. And you see that GR omega can also be written in a very nice, beautiful way, which is d omega prime by 2 pi. And I remember the spectral representation that I derived was some n prime e to the power minus en by t minus e to the power minus en prime by t. And then there was a delta en minus en prime plus h bar omega prime, and then n x n prime mod of this square divided by omega minus omega prime plus I epsilon. So it has this very nice interpretation, as you can see that it has. So this is a very general. This is a very nice formula that you could see for this for the retarded propagator. So you sorry yeah. So you see that because omega minus let me yeah. But so what you can do here is wait. Yeah, you can actually do something, a nice trick, because see, omega prime has to be en minus en prime, right? So there has to be an h bar somewhere. Yeah, so I think I have to. Yeah, there is some h bar that is missing. But anyway, so you could rewrite this. This also will be given to you as an exercise as some n prime e to the power minus en by t minus e to the power minus en prime by t. And yeah, I can forget the delta function and instead put it in the denominator actually. So omega prime would be equal to en minus en prime. So omega minus h bar omega minus en prime. And this overall h bar something that will go up then and then plus I epsilon. So in this way, you could, this is a very nice way to see this, that this is about all the matrix elements of the X between different energy states. And this is the propagator, and this is a weight that you have to see, and this is the Boltzmann weights that you have to subtract of the initial and final state. So yeah, this actually has a very nice structure that we will use later, which I will come to at some point in the course. All right, so now let us try to see a more general property, more general properties like that. So what about the Feynman propagator? The Feynman propagator, g omega. So let us recall the Feynman propagator. G of t is nothing but minus I, the time ordered product of the time ordered product of xt x0 and this expectation value. So I leave it as an exercise for you to do this. So I will give you some hints. So what you need to show in the exercise is that g of omega would always be equal to 1 plus nbe omega times gr omega minus nbe omega ga omega. This is something that you can just follow through all the things that I said before, and you'll be able to see this, right? So if now NB omega goes to minus of theta minus omega when which we showed earlier when so, or we can see this again if you wish. So what is NB? Omega is h bar omega by t minus 1. So when t goes to 0, if omega is less than 0 and then t goes to 0, then this object becomes it becomes infinite, right? And right, it becomes infinite. And so let me see this. Sorry. This object becomes 0. Sorry, this object becomes 0 if omega is less than 0, and then this goes to minus 1. And when omega is greater than 0 and t goes to 0, then this object becomes infinity, and therefore the whole thing vanishes. And this exactly is what theta minus omega is, right? So if I take the temperature t goes to 0 limit, g omega, the Feynman propagator t goes to 0 is equal to simply 1 minus theta minus omega is nothing but theta omega times gr omega and plus theta minus omega ga omega. So again, if you can go back to this harmonic oscillator thing again and look into it, all these expressions that we had are all consistent with this general expectation. Okay, so firstly, you see what is g greater omega, for example. So for g greater omega, in the limit t goes to 0. Now here you see it is omega naught, not omega, that appears here. So when t goes to 0, you will see that g greater omega has support only for theta omega, only for large. Okay, this is something I'm going to come later. Well, so okay, this is something that I'm going to also talk about. But for the moment, I wanted to show the Feynman propagator, which was here. For the Feynman propagator, we also took the g goes to 0 limit, and we saw that. For the Feynman propagator, okay, now I remember we showed it last time. If you remember, we showed it actually explicitly in the last class. So for the Feynman propagator at t goes to 0 for the quantum harmonic oscillator, we showed this equal to 1 by proportional to 1 by omega square minus omega naught minus epsilon square, right? If you remember, and this gives a Feynman plus minus epsilon prescription, but this is nothing but equal to 1 by omega minus omega naught plus I epsilon minus of 1 by omega plus omega naught minus I epsilon, right? If I just simply write this down with an overall factor of 1 over 2 omega naught or something. So you see, this is a retarded propagator, gr omega, but this is only you take it for theta omega greater than 0, and this gives you the minus of ga omega theta of minus omega. So you see that the Feynman propagator indeed at t goes to 0 has this form, and in general also has this form. You can go back to the explicit expressions and check for the quantum harmonic oscillator. Anyway, so this is the discussion that you should actually go and check your notes and try to do it on your own and see, because if we do everything in class, then so just check that this is actually true for the quantum harmonic oscillator from the explicit formula that we had. Okay, so yeah, so this is something that you are going to prove. So one way to see how to prove this thing would be, you try to compute. So you have to say that g of t is equal to theta t times g greater t and plus theta minus t times g less t, right? This is the definition of the Feynman propagator anyway. This is true for any temperature. And it's a definition that comes from time ordering. And here you can use the similarly use the convolution theorem, right? And G greater omega, you can write as minus I rho omega times 1 plus NB omega. And G less omega, you can write similarly minus I rho omega NB omega. You substitute this and use the convolution theorem for Fourier thing, and then you compute the imaginary part of G omega. You will simply say that the imaginary part of G omega. Okay, so it is GR omega. And okay, the other thing that you need to show before is that it's very easy to see that GR omega, you wrote a spectral decomposition for this. Similarly, you can write a spectral decomposition for GA omega. So this is what we get for GR omega. And for GA omega, you have exactly the same thing, except that here omega, this epsilon becomes the minus epsilon. The advanced propagator has a similar, so GR omega we showed is equal to D omega prime by 2 pi rho omega prime times omega minus omega prime plus I epsilon. But GA omega is nothing but the same object. But the only difference is that omega minus omega prime minus I epsilon. And from here, it easily follows that the real part of GR omega is the real part of GA omega. But the imaginary part of GR omega is simply the minus of imaginary part of GA omega, right? So if you combine all of this and you look here, and we already know what these objects are. So imaginary part of GR omega is nothing but minus of half of rho omega, right? So if you use all of this together here, you will be able to so basically the idea is to take this expression, go to Fourier space and compute its imaginary and real part separately. If you do the imaginary part, you will see exactly the imaginary part of this guy. If you do the real part, you see the real part of this guy. We have to use the relations between real parts, and you have to simply use how real part of GR omega is connected to rho of omega and this real of GR omega is. So if you use all of these things together, you should be able to prove this, okay? So this will be an assignment problem. I already gave you a lot of hints. You can complete the proof actually. Okay, so just think about it. You will be able to easily see that this is a general relation and of the Feynman propagator. So the moral of the story is as follows. So we know how to get a retarded propagator and the advanced propagator just from the spectral function, right? From this formulae. And because we know that, we can also obtain the Feynman propagator in terms of the spectral function, right? So that's as simple as that. So all the propagators can be obtained just from the spectral function. That's the main moral of the story. Now, why this is very important is as follows: that if you have some way of computing all of this, and if you just know how to compute the spectral function, then you can compute all of the stuff, right? And often you will see that computing a spectral function is rather easy using and in the Schwinger-Dyson and Quanto, and using this Wick's theorem is often much easier than computing the other things. However, when we go to relativistic field theories, it's often useful just to compute the Feynman propagator itself and not talk about the other propagators at all. But still, if you want to compute any other propagator, like a retarded propagator, you know exactly how to get it from the Feynman propagator. Even so for relativistic field theories at t is equal to 0. If you go to finite temperature, you cannot just compute one of them. You have to talk about all these things together, and you have to. So for these reasons, it is important to know all of these relations, and they apply a lot of short tricks. And also, suppose you have some way to compute things, and any of this relationship is violated. For example, we showed that we have a sum rule, right? D omega by 2 pi omega rho omega is equal to roughly 1, or say h bar. If I put m to 1, for example, or I put this here. So we know that this is equal to 1. And if this is violated, if you have some way to compute this approximately, and it is violated in an uncontrolled way, then you know that this is a bad approximation to, or bad perturbative expansion. You have to do something more to correct. And similarly, we showed that G greater T is analytic for imaginary T in this thing, right? Minus h bar by T less than 0. And you can also show similarly that G less T is analytic for 0 less than equal to imaginary t less than equal to h bar t. So if you validate this relation somehow, if these things are validated in your computations in uncontrolled way, again you say that your computation is not good, your approximation schemes are not good. So these are very fundamental properties that have to be respected in any computation, right? So this is why this is very important to know this. And now in the whatever time remains, I can now give you a proof of this of why rho omega is related to dissipation, or maybe what I should talk about, transport coefficients and the spectral function. Okay, so see that, let's do one thing. Let's try to go back to our what we did in a very early class. So we did that h is equal to some h, not h. So here what I mean is h system. So this is simply the Hamiltonian system. This is not a free Hamiltonian, it's already interacting. Plus some additional small perturbation, which is j dot a, right? This is something that you have to do to be able to go to this. And then so if you use so already proved in earlier lectures, you can go back to your earlier lectures. And actually it's in my notes already. In my note, of course, I took some expectation value like this and computed, say, j, but this is equal to nothing but trace of psi j. And this is also equal to trace in general of rho times j. So you can just repeat everything with this, with a trace of a density matrix instead of an expectation value like this. So if you use that, and if you just simply go back to my notes and see the proof, it is obvious that delta of JIT. So first of all, if you are in thermal equilibrium, there was no current to begin with, because in equilibrium you cannot have any current. So then I can simply take JIT as a whole, and I just compute the linear response in A, only linear in A, and then I get minus I by h bar, and minus infinity to infinity dt prime, and the retarded propagator ij, t minus t prime times the vector potential. So here actually what I'm doing, I'm using a gauge in which I'm setting the scalar potential to 0. I can always do that. Then I only get this term in my Hamiltonian. You have seen this, right? This term j dot a before, this in electromagnetics course. In electromagnetics course, you see j mu a mu is a Lorentz invariant interaction term. Okay. All right. So now if I go to momentum space, frequency space, then I simply get gi omega has to be grij, again the convolution theorem. So a convolution in real time would become a simple multiplication in frequency space, right? And this is what I should get, and there's a minus I by h bar. So, but now what I want to do, I want to write it in terms of the electric field, right? Electric field, I'm using the gauge phi is equal to 0. So electric field E is simply equal to 1 over A dot. If I use the SI units, not my Gaussian units, there's no 1 over C here. So it's simply this. So again, in frequency space, it would imply that E omega is I omega times A omega, right? And
sir, the relation that you wrote, that grij t minus t prime into aj t prime, that response function that we saw, this was derived for H being a free Hamiltonian, and then you perturb it. H system.
No. You go back. No, not at all.
It has H
if you remember,
H naught plus. That's what you wrote in the notes.
Well, you go back to the notes. So this is so I was very careful there, and also in the class I was go back to the lectures. H is arbitrary. This is just a small perturbation. So all that we needed to use there is that you take the time evolution with one Hamiltonian and another Hamiltonian, which are small perturbations of each other. So it doesn't matter whether H is H naught or not.
Okay.
That's all I use. So
Yeah.
I all need to use that this is a small perturbation, and then there, of course, order A square. This is all that I used in the proof.
Yeah.
I didn't use that is the free Hamiltonian. Okay, so if I do that, then I get this, right? And so which means that E omega will be, okay, so then I can substitute this back in this equation, and I get Ji omega is minus I by H bar. Actually, sorry, what I said is nonsense. So this is a sorry, it is simply GR by definition. Yeah, sorry, there is no, sorry, I'm sorry. So the minus I by H bar comes in the definition of GR, not here. Okay, so I'm sorry about this. So there is no minus I by H bar here. Sorry. In the definition of GRIJ is as follows. So GRIJ T will be equal to minus I by H bar. Now, okay, if I, okay, because I don't want to keep the H bar, then I have to keep a 1 over H bar here. Okay, so there's a 1 over H bar. And here there is no minus I by H bar then, simply minus I theta T, and then expectation value of the commutator JIT, comma JJ0. So this is the definition. This is the propagator that I have to look at. So it's a commutator of the two currents, where one current is at some time and the other current is Heisenberg. Now here it is the Heisenberg operator that is being evolved using the exact Hamiltonian of the system, H, okay? This is not the free Hamiltonian, this is the exact Hamiltonian. And this is the thing that we need to compute in perturbation theory. All right, so this is the GRIJ that I need to compute in the field theory. But now if I substitute it back in this equation, I get Ji omega is equal to 1 over H bar GRIJ omega, and EJ omega by I omega, right? So which means that I can simply take the I out and just write it as omega and minus I here, right? So finally what I get that Ji omega will be equal to imaginary GRIJ omega by omega H bar omega times EJ omega plus a part which is real, which is minus I real GRIJ omega by H bar omega EJ omega. So for the moment, what we are interested in is in the real part of the current, not in the imaginary part, because, okay, so first of all, Ji is real, but the Fourier transform is not real, right? The Fourier transform of a real function need not be real. So you only need the Ji star omega is Ji minus omega. Okay, so let us, for the moment, forget this imaginary parts. And so if you go back to the constitutive relation, of J, this is a constitutive relation that we expect, is simply the conductivity times electric field, right? This is what we expect when you take the limit omega goes to 0. So from here, you can easily see that is exactly what should happen. So sigma ij, in general, of course, it can be a tensor, right? But because of rotational symmetry, you can simply forget the ij, because it's only dependent on say, just take any one component. So in that case, sigma has to be, the conductivity has to be equal to, the conductivity, if you remember, is simply 1 over the resistivity, 1 over R, or sometimes people call rho. Okay, I should just use R perhaps, because yeah, usually, okay, if it's a resistivity. So you can write this is basically the Ohm's law, nothing but the Ohm's law, because I, and this is the 1 over R, and electric field is nothing but V by the distance, right? V by D. And then this is This is J is basically the current density, and so this gives you I is equal to V by R. This is nothing but Ohm's law, and so sigma basically sigma is this the conductivity is 1 over the resistance is simply the limit omega goes to 0 of imaginary part of GRIJ omega by H bar omega. Now you see it has a classical limit because imaginary part of GRIJ is nothing but a commutator. The commutator always is order H bar. So by H bar, it will have a classical limit. And you take a division by omega. You have to also take a division by omega. And then the limit of this would give you the conductivity. But actually, if when in the derivation, what we have done, in a derivation, we have actually taken the limit k goes to 0 first. So actually, because so what you mean is that you have to first take the thermodynamic limit where you take k goes to 0 and then omega goes to 0. And if I reinstate k, it will be omega k by H bar omega. This is the actual formula. It's often called the Kubo formula for conductivity. Okay. But you can worry, what about this guy? What is happening to this? What does this mean? This actually will be related to the capacitance. You can wonder whether this diverges when omega goes to 0 or not. So there is actually a divergence which actually gets cancelled. And that's because I have cheated you a little bit. The cheated you by saying that J, okay, so not exactly cheated you. The thing is that this formula which I wrote is slightly problematic because in real life, so if you look at the actual action of a material, the actual current, say, the actual current in the present of the A field is not simply psi dagger, say minus I grad. There is also a minus EA psi, right? So what happens is that the actual current operator, so this is what I defined by the current operator, psi dagger minus I grad psi is a current operator. And but there is also this extra term, which is called a diamagnetic term, which is EA psi dagger psi. And this actually gives rise to an extra contribution to the current. And now in a material, when I take the expectation value of J, right, then this, of course, will be given by the retarded propagator. This part has no expectation value in thermal equilibrium. So it's given by the retarded propagator times whatever this A that I wrote down. But then this object will have a natural expectation value, which is rho, because this object is simply the density operator. You have some kind of a rho. There is already some EA rho that sits here. What you can show is that this EA rho term, if I take that into account in definition of the current, and this divergence cancels out here, but this is a little bit of a complicated story. Maybe I should come back later when I actually go to field theory. So for the moment, if you don't follow this, is fine. But anyway, what you can show that this is basically related to the capacitance of the system, and you can basically go to the RLC circuit and show that this is actually exactly what to expect from the RLC circuit as a response to an electric field. All right, so sorry. Okay, so in the last part, I would just simply try to show how you can get Ohm's Ohm's kind of dissipation. If you remember that, if you go to high school, you see the power that is the electric dissipation. I think you have seen something like half Ri square, some formula like this, right? So let us see where it comes from, actually. So actually, it comes from basic quantum mechanics and quantum algebra. So this is, so the Hamiltonian is equal to H system plus J dot AT, right? So now, so dH dt has to be equal to del H del T. Now you see all of these are operators, but this is an external field, right? So dH dt is nothing but J dot A dot T, right? And A dot T is nothing but the electric field in whatever gauge I'm using. So this is minus J dot E. Now, but J is something that we saw was equal to this. So if I write it down explicitly, and suppose okay, let us see this dH dt explicitly should be equal to then minus GRIJ. So maybe I should write down the this is dt prime minus infinity to t, and then I simply write what is j explicitly. It's jrij t minus t prime, then aj t prime, and then I have a eit, where eit of course can go out of the interval. But now what I should do, I should integrate this the total loss over a period and take an average. So suppose the thing is that I should think of electric field as some kind of e to the power I omega t times some e naught omega at a single frequency, and I take the time period is simply 2 pi by omega is equal to the time period. I just simply take a integral over a time period and take that to take the loss. And then if I do that, I will actually have to do this integral 0 to t, and then dt prime would be then from 0 to small t, and then you have a theta here and everything. So I don't want to go through all the details, but you can but okay, let me sort of quickly tell you. And grij t minus t prime, aj t prime, and ej t. But again, you can convert this to a frequency integral, and the frequency integral would be looking something like this: d omega prime. But now you can put in a factor of half. Okay, so this is yeah, it comes from this. Yeah, for the moment you could think that I don't have a theta function, but you could get rid of the theta function by simply taking 0 to capital T and putting a minus half, because by symmetry you can do that. If you do that, then it becomes an integral of this kind: d omega prime gr omega, and then mod of ej omega square. And because I can write this as a as 1 over I omega, and then I have a 1 over I omega here. Now, the real part of the gr omega is actually an odd function, is an even function, because you can go back to this definition of real gr omega was rho omega by omega minus omega prime. And this rho omega prime is an odd function. This is also an odd function. So you can show from this definition is an even function. Gr omega is even in omega, which means that real gr omega is equal to real gr minus omega. So so now when you do this integration, you will see that this the real gr doesn't contribute, and the contribution comes only from the imaginary part. So essentially the dissipation is always and this integral will be always positive, because rho omega by omega is so anyway, to conclude, you will see that this is half of t omega d omega prime, and imaginary gr omega by omega mod of ej omega square. Okay, now you see that the imaginary gr omega by omega is always less than 0, because this is rho omega, and rho omega is minus of rho omega minus. So essentially you see that this is, so you always get a minus sign here. So it means that the energy of the system is always going to decrease. The system is going to dissipate it, right? That's the meaning of it. The system will always dissipate it. And okay, there is no d omega prime. I think I wrote this d omega prime for no reason, because of, yeah. So here, okay, I will just simply say what is the steps that went in. So here I use convolution theorem to do the dt to go from dt prime to d omega, and then the Percival's theorem, and then I got this. That anyway, so you can go through the steps. I was quick, but then imaginary gr omega by rho, but it's simply this part would give me the dissipation. If you remember, this gives me imaginary gr omega by omega gives me the conductivity sigma times then ej square, ej omega square. So now if I convert, so suppose this is the integral of dh dt. So if I now take the limit where omega goes to, if I take that long time period, you can easily see what I get. From here, I should get 1 over r. Sigma is 1 over r. And then I can substitute this. This is to be I, this is basically equal to, wait, have I done something fishy? No, this is up to here is fine. And I got sigma will give me 1 over r, and E would be equal to J by sigma. So it will be R times J. So R squared times J square, right? So which is basically the current square. So if I take this object together, this will be proportional to basically Ri square, half Ri square. So this is exactly the Joule heating that you get, right? This is the Joule heating that we that is a dissipation that we see in the system. So so let me just be careful about signs. So let 1 second. I think I may have made small error in some sign somewhere, because sorry. Now, what I'm worried about is as follows, that this sigma should be positive, but imaginary GR is negative. Imaginary GR by omega is negative. So I must have made a sign error here somewhere. Where is the sign error? Maybe I made the error here in A dot. E is equal to minus A dot. It should be I omega. No, but this is correct, because if I go to frequency space, this is A omega e to the power minus A omega t. If I write it in terms of omega, so it should be minus I omega minus, this becomes 1. And then I get here 1 over I omega. In terms of 1 over I omega is minus I. That was also correct. And this is the Kubo formula, h bar omega, imaginary GR ij omega by h bar omega. But there seems to be some small error somewhere in some I or something I've not taken into account. Okay, let me check from my notes if I could figure this out. One second. Oh, I'm making some stupid error somewhere. Yeah, I think. Yeah, I think the mistake is probably here, that it should have been an I instead of a minus I. So let me go back and see. So what I did was I got a 1 by I omega, and this became a minus I omega, but it should have been I on top. So what is the mistake? Oh, probably this is the mistake I made. I think the Hamiltonian here should be minus J dot A, but I can check. This is the mistake I made, probably. The Hamiltonian itself of a minus J dot A instead of plus J dot A. Yeah, that is should be easy to see, because why? Because yeah, so that is, so I should simply go and check the in the action. When you write, the action comes like J mu A mu. So that happens in the action. So in the Hamiltonian should be a minus J. Okay. So this is a mistake. So then there should be an overall minus sign here. Okay, thanks, I found it. So there should be an I then, and then there should be a minus and there is a plus. So then the only thing is that I should put a minus sign, right? And wait, so if I do the minus sign, then that is correct. Then I should have. So here I was getting 1 by I omega, and similarly I got. Yeah, I have to now check the signs carefully. So here also I made a sign error. So there's a minus j dot a. So there should be a minus j dot a and plus j dot t. So it should start with a positive sign. Yeah, so sorry, I think, yeah, okay, so sorry, then this sign should be positive and 1 over I omega. So this is imaginary I, and the I gets cancelled. This is positive. So this, I forgot the sign anyway. Yeah, so the sign should be such that the system should heat up, right? System should heat up continuously, because if you connect a system to a infinite bath, it can only take energy from the bath and heat up. That's the only thing that can happen. So okay, so the thing is that, okay, so the thing is that sigma should have been minus imaginary grij by h bar omega. Now this is going to be positive, right? Because rho is negative, sorry, rho is positive, but minus of imaginary gr is rho, right? And minus half of that. So therefore, this has to be minus. And here, similarly, that's because I goofed up the sign in the Hamiltonian. And then similarly, if I write it down in the correct way, if I write the correct expressions, this is 1 over I omega, and this becomes rho. Okay, gr. This is, so we get this, and yeah, because this is real plus imaginary, the I will cancel, and imaginary gr, and yeah, so I get the correct sign. So this is positive, right? So because the system has to always get heat, which is greater than 0. Okay, so this is so in the limit when omega goes to 0, the joule rate of heating will be half r I square, half r I square. So this is basically the joule heating that you derive from here. So the main thing is that you get back high school physics. That's very interesting, but the high school physics comes from a deeper understanding of the operator algebra and how stuff actually fundamentally work at a fundamental level. So this is beautiful. So I think you should appreciate this. And you also see how to correct high school physics, right? How to make a very improved understanding of dissipation and conduct and transport from quantum field theory. All right, so that's the end of today's lecture then. And I wanted to do also Euclidean propagator, but maybe I can do it very quickly next time and start with the proof of the Weeks theorem. Okay, so any short question before any questions before we conclude? Okay, if not, then let me stop today's recording, and then where is this stop recording button? Yeah.